Welcome everybody to this presentation about dynamic power measurement and accelerated efficiency mapping. My name is Alexander Stock. I'm with HBK as technologist in the field of electric power tests since June last year. And before that time, I was research assistant at the Technical University of Applied Sciences in Aschaffenburg, where I was investigating in the field of dynamic electric power measurement, also in a strong cooperation with HBK. And during that time, I also did the Comparative doctorate with the University of the German Federal Armed Forces in Munich, which was also about dynamic power measurement, especially in e-drive applications. So I was investigating in the field of power theories, measurement equipment, and all around that topic. First of all, I would like to introduce HBK, who we are. HBK was merged in 2019 from the two companies Brüel & Kjær, B&K, and HBM, Hottinger Baldwin. And both companies are experts in test and measurement applications. Brüel & Kjær has his background in sound, noise, and vibration measurements and analysis, whereas HBM was operating or is also operating in reliability, durability, propulsion, efficiency, electrical properties, and weighing applications. Whereas Brüel & Kjær therefore mainly uses frequency domain analysis, HBM is a specialist in time domain approaches. And for this reason, it is of course very suitable to combine that knowledge in order to cover the complete measurement chain, including sensors, data acquisition systems, but also the preparation of measured data, the evaluation, simulation, and engineering. Of course, it's possible to group the different physical domains where we have our expertise and knowledge in measurement technique. But of course, depending on the application, those groups or domains are always strongly interconnected. We have the mechanical domain with the subdomains strain, force, load, pressure, torque, durability. We have the sound and vibration domain with noise, sound, power, sound quality, acoustics. And we have the electrical domain, of course, with the subdomains of electrical quantities, so the voltages and currents, but also speed and temperatures. And the interconnection of all those different physical domains will get clear during the presentation as well. And this is where we can benefit as one HBK from the two different or separate experience which we now have combined in one company. With this background knowledge, I would like to give you now an overview of the main content of this presentation. At the beginning, we will have a look on the typical topology of an electric powertrain. Which quantities are relevant, what should be measured, how should we measure this in order to do an electric power calculation. In the first step, we will do this with a well-known conventional method based also on standards. And then in the second step, we will see how we can make use of a dynamic electric power approximation, which is very suitable, especially for highly dynamic applications, of course, such as robotics or automotive. And we will see the benefits of this novel approximation method based on comparative measurements. And I will then also connect in order to show how this method may be used, for example, to do an accelerated efficiency mapping. So how the benefits are for the application. And I will finish the presentation with a short summary and a conclusion. So as mentioned, first of all, an overview of the typical topology of an electric drivetrain. We have here the electric machine. This electric machine is fed by an inverter, and the input of the inverter is typically connected to a power source. If we think again about the automotive application, the power source would be the battery. And the inverter is used to transfer the energy from the power source to the machine, of course, in a suitable way, and also in the other direction during generator operation. So if we think about a car, for an acceleration process, the electric machine consumes energy. during recuperation, during electric braking, we can save energy loss and we can transfer the energy from mechanics back to electrical quantities into the battery. And in order to optimize the efficiency of all those three components, so the energy storage, the power electronics, and the electric machine, but also of the overall drivetrain, we need to get relevant information. And this information is, of course, measured data. And for that, we use here, in this case, a Gen 40B, so a raw data acquisition system, in order to collect all this relevant data time synchronously. There may be an additional measurement PC connected to this system in order to set up the measurement settings or to visualize the measured data to do further analysis. But the system may also be connected to an automation system, which is then again connected to the inverter control, probably, in order to define new set point values, for example. So now, what we should do in the first step, we should take a look on the relevant quantities which should be measured in this drivetrain. This is, on the one hand side, of course, the electric output, so voltage and current, output currents of the battery, but of course also of the inverter. And in order to be able to calculate the efficiency of the electric machine, it's also necessary to measure the mechanical output of the machine, so torque and speed at the shaft, which is measured here with the torque transducer. And for several reasons, for example, for safety, but also in order to check if temperature conditions are constant, for example, during an efficiency mapping, it's important to get the information about temperatures. This may be winding temperatures, but also temperatures of the power electronics and the energy storage. And some of our customers are also interested in measuring vibration signals or acoustic noise signals generated by, of course, the high frequency components, which comes from the inverter, for example, but also mechanical oscillations coming from the mechanical drivetrain. There are a lot of different sources which create vibration and acoustic noise. And the challenge is to measure all those signals time synchronously in order to be able to do further analysis on that, which helps to optimize the drivetrain. And now, in the first step, since we are talking about electric power measurement today, I will discuss how to measure current and voltage correctly in a suitable way. And therefore, I would like to show you that based on a very general diagram topology. We have here an N-phase system. And in practical measurements, this N-phase system could, for example, be an electric machine. It could be an inverter. It could be the combination of both. And as you know, there are three-phase machines, multi-phase machines. So in general, you have a certain number of conductors which are connected to that system where you want to calculate the power. And in order to do correct power calculation, all conductors connected to the system, but also contributing to energy transfer, should be considered for power calculation. So this includes, for example, also a neutral conductor if this neutral conductor is connected to the start point of the machine. But it does, for example, not include a CAN communication of the inverter, which does not contribute to the energy transfer in this drivetrain. And for the currents, it's quite clear we have to measure the currents in the conductors connected to that system. But for the voltages, there are different possibilities. The voltages may be measured against different reference potentials. So in general, there is a possibility to measure from each of the relevant conductors the voltage against an arbitrary reference potential here, which is in this case called R. And it's of course also possible to measure voltages between the phases, so from phase 1 to phase 2, from 2 to 3, and so on, and at the end from the last phase back to the first. But as you can imagine, a different voltage reference potential may also lead to different voltage RMS values. But in order to get consistent active and reactive power results, we should, in the first step, always calculate ideal natural zero voltages. And natural zero voltages are the voltages which could be measured against such an ideal artificial star point, which is a nicely balanced star point with equal resistances. And therefore, not only the currents which are going into the N-phase system sum up to zero due to Kirchhoff's law, but also the voltages measured against such an artificial star point. So as just mentioned, in practical measurements, there are a lot of different ways to measure against an arbitrary potential. This could be in practical applications, the neutral conductor, ground, star point of the machine. There are a lot of different possibilities. But in order to make sure to calculate consistent quantities, not only for instantaneous and active power, but also for apparent and reactive power, in the first step, it's always useful to calculate natural zero voltages, which of course sum up to zero. What you probably also know about is the fact that if you measure those zero-sum quantities, it can be enough, depending on the application, that you measure for an N-phase system n-1 quantities, because you can calculate the last one which you did not measure. This is, for example, the case if you think about the Aaron measurement circuit for three-phase machines. But these are special cases, and also for them, typically in the first step, the ideal zero-sum quantities should be calculated. Now you can see here how we solve this issue in our software, in Perception and the included eDrive sheet. And of course, independence of your measurement, of your real measurement setup, the user defines his or her measurement setup. And the voltages could, for example, be measured against any arbitrary potential or to ground, phase to ground, like in the left picture. Or we could, for example, measure phase to phase. But there are, of course, a lot of different other methods. I only have chosen those two examples to show you how everything works. And then, of course, the customer does not have to do this on his own. Then in the background, the formulas to calculate these ideal natural zero voltages are calculated automatically. And of course, this depends on the measurement setup you have chosen and you have wired your real setup. So you can see here, the zero system is subtracted. Of course, that's a bit different if you measure against a common arbitrary reference potential, or if you have different references like for phase-to-phase measurement. But nevertheless, it is possible and it is done automatically in the background. It's only important to choose the correct setup and to wire the real hardware like the setup provides. Now, after having discussed how to measure voltages and currents correctly, I would like to take a look how in a second step then power quantities are calculated based on the measured voltages and currents. Therefore, I would like to take a look here again. You can see the same topology like on the first slide. We have here a battery, we have an inverter, and we have, in this case, a three-phase machine, also a torque transducer. And since you are talking about electric power, I have now chosen as an example the electric input power of this three-phase machine. Therefore, you have to measure the input voltages and currents of the machine. So the natural zero voltages, or if you measure against another potential, these voltages are calculated. And of course, the three-phase currents. And you can see the measured quantities here in this picture on the left bottom side. As you can see, the inverter output voltages, which are the machine input voltages, as long as you neglect conduction losses in the conduction wires over here. Otherwise, you would have to measure the inverter output and in the machine input in order to calculate line losses, for example. But for simplification, we neglect the losses in the conductors. And we have here the inverter output voltages. And of course, due to the functionality of an inverter, this inverter output voltages contain the high frequency content, which is related to the inverter switching. So the steep switching edges an inverter typically produces during operation. And therefore, the inverter output voltages are disturbed with this high frequency content, by functional principle. But since the electric machine typically represents highly inductive load, the machine currents are much smoother. Of course, you can also see, if you would zoom in here, you could also see that you have a kind of high frequency content in the currents, but the currents are much smoother compared to the voltage in a lot of typical applications. And what you should know so far is that for the power calculation, we need to average instantaneous values over the fundamental period of the electrical measured quantities, so the voltages and current. So what should be done in the first step is calculate the fundamental frequency / period of voltages and currents. And this is much easier if you do that based on current evaluation, because the current, as mentioned, contains much less harmonic content and is a smoother waveform. So, of course, there are different ways how to do that. You could use phase lock loop circuit, which may, during balancing processes, lead to a time delay and phase shift. And we solved this with a zero crossing detection. Of course, the crossing detection must not be around zero, but in typical applications, the currents during steady state are oscillating around zero. And you can see that over here. This is one of the phase currents, the blue one. That's the current phase 1 of this three-phase machine. And we look for zero crossings. And then we get this purple curve representing the cycle signal. And the period length of this purple rectangular waveform, this is one fundamental cycle. And this is the basis for all cycle-based calculations. So not only active power, but also apparent power, reactive power, the calculation of RMS values, but also of efficiency and power factor, for example, or fundamental waveforms. All those quantities are calculated based on this fundamental cycle. So it's very important to have robust fundamental cycle detection in the first step. Now, since we have the measured quantities, the voltages and currents, measured correctly in a useful way, we detected this cycle over here. Then we should have a look on how power is calculated. So this is well known from basics, that the instantaneous power in each phase is equal to the product of the corresponding measured voltage or natural zero voltage and current. And this should be done for each phase. And at the end, in order to get the total instantaneous power, you should sum up over all phases. And then in a second step, this is what we've discussed so far, we have to average over the fundamental period. The fundamental period is this T, so it's a time average of this instantaneous power over the fundamental cycle we have detected here, this cycle. Here is one period. And this averaging is done in order to calculate active power. Now we have discussed the basics, how to calculate, how to start from measured quantities to the power result. Now I would like to show you how that is again done in our ePower suite. There you can again see the typical topology, the power source, but also the inverter, and here a motor. And on the right bottom side, you see the typical information which you know from conventional power meters. So the active power, reactive power, apparent power per phase, also the RMS values of voltages and currents, power factors, cosine, phi, and everything. It's there are a lot of useful information. You can see that over here. But what you get in addition is you can see here the waveforms of the measured quantities. You will see them also in real time. So the voltages and currents, the inverter output. But you could also see all other calculated quantities. This is only here on the simplified standard sheet. You can have much more information. And you can see here the add blocks. So you could add components and build up this basic topology, which is only, as I said, a very basic topology. You could build up your own customized user-defined topology. So for example, you could have here two machines which are operating on the same shaft, fed by perhaps two different inverters, which then are connected to the same common input power source, for example. So it's completely flexible. And all those power calculations which we have discussed so far are then implemented in the background automatically. Independence, of course, of your measurement setup you have customized. And you can see that over here. In the first step, of course, we have an allocation of the measured quantities. Then we do the very important cycle detection. So I show you this slide not in order to have a detailed look on all those lines, but in order to show you that you can realize the step-by-step procedure I've just explained, that we do that in the background. And you can see here again also the power calculation. So the multiplication of voltage and current per phase, summed up over all phases here. And then we do averaging per phase in order to have per phase active power, but also the overall active power. And this is, as mentioned, done automatically in the background. But if you, for example, have an application where you say, okay, in our special case, it is suitable to do it in a different way because of etc., then you can, of course, insert your own user-defined formulas as well and evaluate those ones. That's all of about the conventional way of power calculation. And now I will go on with the special topic of today, the dynamic power approximation. And therefore, we start again with the same topology as before, and we also take the same measurement. We have again the three voltages and the three currents at the input or output of the inverter or input of the machine. You can see the same picture over here, but instead of calculating the fundamental cycle based off one of the currents, we now calculate the switching cycle, so the switching frequency of the frequency inverter, by applying a powerful detection algorithm on the inverter output voltage. And what you get as a result is here the switching cycle. And this is typically in a lot of applications up to several hundred times faster. Because if you think about, for example, an inverter switching frequency of 8 kilohertz and a fundamental frequency of 50 hertz, then there is a factor of 160. And the idea is now to use this fast cycle instead of the fundamental cycle for all cycle-based calculations. And of course, one could ask in the first step, is that a suitable way? And I will explain that it is, and we will see that later on based on measurement examples. But in the first step, coming back to the process. So what we do now is we have again here the small p, the instantaneous power, which is again averaged. So it's the same formula like before. The only difference is that we do not use the fundamental period as averaging interval, but the switching cycle, the TS instead of T, which is, as discussed in typical applications, up to 100 times shorter. So the update rate is increased drastically. And this provides an approximation of the conventional active power definition during steady state. That's one aspect. But in addition, this combines the conventional steady state information with additional instantaneous power information during transients. And all this information is combined in a kind of new power definition, the dynamic active power. You will see that named as P dynamic. And the quality of this approximation becomes better the larger the fundamental period is compared to the switching period. Or in other words, for higher switching frequency compared to the fundamental frequency, respectively. And that this is a useful way to do it this can be proven mathematically, not in this presentation today, but it can be shown that for the theoretical case of infinitely high switching frequency and some restrictions or considerations with regard to the generation of pulse width modulation of the inverter control, the equality of both methods can be proven mathematically. And in practical applications, it's a very powerful approximation as long as switching frequency is much higher than the fundamental frequency. So now I want to show you, based on different measurements, where the benefits of this new fast approach are. And for this, I want, in the first step, take a look on a startup process of a permanent magnet synchronous machine. Startup process in this case, in this context, means startup from standstill to a certain constant steady state speed without any load in the first step. And of course, as always, what should be done in the first step is we take one of the phase currents, here the current in phase 1, and this phase current is used for the conventional power calculation method to define the fundamental cycle. We can see in the bottom plot the instantaneous power here. Of course, this instantaneous power, the blue curve, is disturbed by the high frequency content of the inverter output voltage. So of course, this quantity contains a lot of information, but it's difficult to visualize it in the instantaneous power. It does not give a good feeling for averaged energy transfer during the startup process. That's the reason why we typically calculate active power quantities. But as you may have realized by principle, since we calculate active power over the fundamental cycle, so as a time average of instantaneous power over the fundamental cycle, of course, in real-time applications, the averaging process may be started with the first positive slope in the cycle signal here, the positive edge here. And then, of course, we have to wait until one fundamental cycle. And here at the end of the first cycle, all the information from here, from this averaging process, may be used to now, but we have to wait until we have found the first full cycle, and then we can calculate the first active power information, which in real-time applications is then shown for the next fundamental period. And that's the reason, if we do it the conventional way, where you get the first active power value here after the first full cycle has been detected, and for the next fundamental cycle. This is limited by principle, by causality. We have to wait for one cycle in order to calculate at the end of this cycle the average of the information collected in between the cycle. If you would average, or if you do the dynamic approximation, the latency is only one inverter switching cycle, which is very fast, especially at the beginning, where fundamental cycles are, due to the acceleration process, quite slow. But the switching frequency may be high directly from the beginning. And for this, you can see here the red curve, which is the dynamic active power. And it includes the harmonic content. Here you can see the dynamic of the energy transfer per switching cycle of the inverter. And it gives you drastically increased dynamic update rate and active power information. So this is what you get from that slide. If you compare this, the conventional active power gives you the first value after the startup process has been almost finished, whereas the dynamic approximation method gives you a nice information about dynamic energy transfer. Now we take a look on the next example. This is not a startup process, but a transition between two different steady state operating points. What should be mentioned at the beginning is this measurement was done for a constant speed. And on the left top plot, you have again the instantaneous power with all the high frequency content. And on the bottom plot, you have again both active power quantities, the conventional one and the highly dynamic calculated one. And what you can get from the sign of active power is that at the beginning, with the negative value, we are in a generator operation. And then after this dynamic transition, we have a constant steady state motor operation. And this was done by use of a load machine. So the device under test was speed controlled with constant speed, and the mechanically connected load machine was used to generate a load torque. And by changing for a constant speed, not only the value, but also the sign of the load torque, we can go from generator to motor operation. And this is done here in this measurement. And what you can get from this measurement is that during the steady state, so here in this middle area of the plot, but also on the left-hand side at the beginning during generator operation, both active power quantities are quite equal. So the approximation is very powerful. To mention in this context, it should be mentioned that the switching frequency was approximately 100 times higher than the fundamental frequency to get this result. But you again see also the benefits, which we discussed already on the slide before. During the balancing process, of course, the conventional active power has this stairwise waveform, which is related to the long time averaging interval of the fundamental period, whereas the dynamic active power includes also transients, which are coming from the inverter control, and also the peak values, the overshoot. And you see much more dynamic, but, and that's important here to know, a very precise approximation during steady state. Now we have seen the differences and advantages of dynamic active power during highly dynamic applications and balancing processes, but you can also transfer the methodology to other quantities than power. For example, you can calculate dynamic fundamental quantities. And we have now again a look on the startup process. In the top plot, what you have seen now the third time, but it's important to have it here time synchronous in this picture. We have again the detection of the fundamental cycle based on one of the currents. Then you can see in the second plot one of the inverter output voltages, which is of course, contains the harmonic content of the switching frequency and looks like a disturbed, by principle disturbed waveform with high frequency content. And if we now average this inverter output power with the dynamic method, this gives you, so based on the inverter switching cycle, you get as average here this blue waveform. And if you would have a pulse width modulation, which includes some zero systems, for example, third harmonic injection or also other flat top modulation, for example, then it would be necessary not only to calculate in the first step the average of the inverter output voltage based on the switching cycle, but in the second step, subtract again the voltage zero system. If you use ideal start point, this is subtracted automatically. And if you compare that average, which gives you an impression of the fundamental inverter output waveform, if you compare that with a conventional method, then we have again the same effects. The conventional fundamental voltage calculation based on a Fourier series also depends on the fundamental period. And therefore, you can get the first value here after the first full cycle has been detected. But there are a few more issues. One is that during the startup process, the frequency and the amplitude of the inverter output voltage increases continuously. Therefore, the quantities are not periodic. But if you think about standards of power calculation, fundamental calculation, all definitions which depend on the fundamental cycle, they are in a strict sense only defined for periodic quantities, so for steady state conditions. Now during startup, there is no steady state condition. So the conventional method is in a strict sense not defined at all, and you can see problems due to the frequency increasing continuously. The zero crossings are not at the correct position, and at the beginning and end of the periods, you may have steps because also the amplitude of the voltage waveform increases continuously. And yeah, but you can choose the dynamic approximation to get the better results, also again, including transient peaks. And what you could do with those fundamental waveforms, which you have calculated dynamically, you could calculate from that fundamental space vectors. So if you take the three linearly independent quantities and you do a space vector transformation, which is also known as Clark transform, then you get the two orthogonal quantities, the U alpha and the U beta, if you are talking about voltages. And the question is, why should we do that? On the one hand side, this is a very powerful tool in order to assess, for example, inverter controls. And you could also do fundamental DQ0 transform, which could again be used to assess the inverter control. But you could also calculate, if you interpret these both components as one complex space vector, and you calculate the length of this space vector, which is equal to the magnitude, then for sinusoidal quantities, and since we are talking about fundamentals, these are sinusoidal quantities, then the length of the space vector is equal to the fundamental amplitude. And if you have a balanced three-phase system, and you calculate in the first step the three fundamentals of voltage and of current, and for both the amplitudes, then you can calculate the fundamental amplitude of voltage and current of a balanced three-phase system within the first switching cycle. And that's quite powerful. And you can see that over time here in the left plot, again, with the same that we have the dynamic information. And here, the conventional one gives you here some straight oscillations instead of a nice step. This is related to the fact that during startup, the voltages are not balanced. You have an unbalanced system, so the amplitudes of the different phases may be calculated in a different way with the conventional method. And if you do that, then you can, in the next step, calculate from the fundamental amplitudes the fundamental RMS values. Because for sinusoidal quantities, that's quite easy. It's a division by square root of 2 to get the fundamental RMS values. And you can see that in the picture on the left side over here, in the first plot for the voltages, in the second plot for the currents. And if we take a look, a detailed look here on the voltages, the blue curves is the RMS value of the inverter output voltage, including all harmonics. The yellow curve is the RMS value of the fundamental of the inverter output voltage. So only the fundamental RMS calculated with the conventional method based on the fundamental cycle. And the red curve is the dynamic approximation. And you can see that again also for the currents. And of course, here in this context for a load step. So you can see based on the current that for a constant speed, again, the torque was reduced, therefore the current goes down. But you can see again the benefit of dynamic information for the dynamic approximation, whereas you have this slow decrease of RMS for the conventional definition. Since most of the relevant part of active power is transferred in the fundamental, if we talk about inverter FET drives, this is related to the fact that the currents are more or less sinusoidal. You remember there was only a small amount of high frequency components. Therefore, the total RMS is more or less equal to the fundamental RMS, not absolutely, but more or less. Whereas, of course, the voltage, there are a lot of high frequency components in it related to the inverter switching. And therefore, the total RMS differs strongly from the fundamental RMS. And with this information, or with all these RMS values of voltage and current, one could then calculate based on the RMS values also dynamic apparent power. And since we discussed in the first step dynamic active power, we now have dynamic apparent power. We can calculate as a geometric difference also a dynamic reactive power. On the left side, we have again the same picture as for voltage and current RMS values. You can see all the quantities, and the blue is always the conventional definition, including all harmonics. The yellow is the conventional definition for fundamental quantities, and the red one is the dynamic approximation. And you can again see the dynamic approximation is a powerful approximation of fundamental quantities during steady state, with great benefit of giving much more dynamic information during the transient balancing process. And after having shown all those different possibilities, what could be analyzed with a dynamic method, I would now like to go back again to the application and to show you how you could benefit from this dynamic application with regard to the application. And therefore, I want to take a look on a dynamic efficiency mapping. If we think about efficiency mapping, this is typically, if we take again a conventional method, this is done step by step. Typically, the drive is operated at different constant speed and constant torque operating points. Of course, the number of operating points depends on the level of interest of the user, of the whoever does this measurement. But it is important to have steady state operating points and to evaluate those different steady state operating points sequentially. And if you do that, one method could be the machine could be operated at a constant speed over here. And for this speed, sequentially, all different torque values of interest are again driven sequentially. And then for each of these torque speed combinations, the measurement system or the inverter control should be operated. Then the measurement should be done, but it should be started only after the balancing process from the previous steady state operating point has been finished and the new steady state operating point has been reached. So typically the inverter control goes to a new steady state operating point, gives the feedback to the measurement system when the new steady state operating point is reached. That takes some time. Then the data acquisition is started. And after the data acquisition has been started, one has to measure for a certain number of several fundamental periods. Then the measurement is stopped and the inverter may drive to the next steady state operating point. And during this measurement, of course, all relevant parameters such as the RMS values, or if we talk about efficiency mapping, the active power quantities are calculated. And this takes, of course, a lot of time because you have to drive from one steady state operating point to the next one and always wait until really reaching steady state conditions. And of course, this here is only to show the procedure, but in reality, you have quite a lot of different torque and speed combinations. Of course, for high speed values, perhaps not all torque values may be driven to because the maximum power is limited, but from the procedure, it is like this and it takes quite a lot of time. If we talk about the dynamic method, then this time may drastically decrease. And the reason for that is that the measurement is not restricted to steady state conditions. And therefore, if we take a look on the diagram again, if we would drive to a constant speed value, we could increase the torque from 0 to the maximum value we want to consider continuously. So kind of sawtooth function here for the set point value of torque. And also the restriction that we have constant speed in this measurement, this is not a general restriction. We will see later on a measurement where this was done like this, but the reason for that is only to be able to compare all different torque speed combinations. So to have a plan that really all torque speed combinations are included in the measurement in order to be able to compare the results. But in general, there must be no steady state conditions, not in speed and also not in torque. And this brings, as you can see from this set point diagram directly, a lot of time savings. And the time saving is, of course, increased the more values you have. And typically, you have quite a lot more than here in this simplified diagram. So if I show you now the results of these measurements, we come here to this next slide. On the left-hand side, you can see the measurement result of a permanent magnet synchronous machine efficiency map, which was in the first step here done with a conventional method. So what you can see as red circles are the steady state operating points with a constant torque and speed. So you can see here for this speed, we had 1, 2, 3, 4, 5, 6, 7, 8 torque values. Then the speed of the drive was increased to the next constant speed. And again, the drive was operated at more or less the same torque values. And this was done for the whole map. Of course, this part here is missing because this is the area where the machine power is too low and we cannot drive to this area. But nevertheless, you can see the procedure. And yeah, you get as the color of this contour plot, you get the efficiency value. So the maximum efficiency here is 94%. Of course, this is not highly sophisticated drive, but it is good to demonstrate how the procedure works. And yeah, you can see the result. And now we do the same measurement, but in a separate measurement. So sequentially, not in the same measurement, because the procedure of measurement is completely different. For this right diagram, the machine was again operated at the same speed values, but instead of driving to individual steady state torque values, we increased the torque continuously for each speed. And then, of course, we did the evaluation based on the fundamental cycle, but based on the inverter switching cycle with a dynamic method. And by this, you can see we get as a result a high level of similarity, but for enormously reduced measurement time. Of course, the result is not equal because dynamic active power is, as the name says, an approximation. But the measurement time can be reduced drastically and the level of similarity is quite high. And it gets even clearer if you compare, if you can imagine that over here, if you calculate the difference of both of these plots. So the absolute value of the difference, this results in this diagram here on the right-hand side. And you can see that in all relevant areas, the deviation of both measurement results is less than 1%. In most of the areas, even less than 0.5%. So if you require highest level of accuracy, of course, go for it with the conventional method. But if you want to do dynamic efficiency mapping, for example, in the context of end-of-line tests, where you want to decide, is the machine okay? Is the maximum efficiency of 95%, is it realized? Yes or no? Then you have with the accelerated dynamic efficiency mapping a method which can save a lot of time and, of course, therefore a lot of costs, of resources. And it could also be included, for example, in a WLTP measurement, because you are not restricted to steady state conditions. So if, and I think most of automotive manufacturers do that, they do the WLTP test scenario. And if you do that, you can get out of this WLTP test, in addition, also an efficiency map. So you can save a complete separate measurement. And that's a real huge advantage. You have the time reduction and you can probably save a complete measurement. And yeah, that is one very useful practical application for dynamic power measurement in this context. So this is most of that what I wanted to show you now so far, but I would like to give you, as mentioned, a small summary. We have seen at the beginning that there is a dynamic active power, which was introduced as a new kind of power definition. It combines the characteristics of instantaneous power, but also of active power during steady state in a new power quantity. The basic procedure can be used also to calculate other cycle-based parameters such as RMS, reactive apparent power, power factor, fundamental quantities, and a lot of more. And you can use the dynamic power to do an accelerated efficiency mapping. And therefore, you can save resources and costs. And you could probably include the efficiency mapping in another test, which has to be done anyhow, for example, the WLTP test. And there are a lot of different other applications here. I mentioned two, which were investigated at the University in Aschaffenburg, but that is mentioned for reasons of completeness. I see that we are good in time now. I finished the presentation so far. So if you are interested in this and all other related topics in the field of electric power test, we are happy if you join us on YouTube or LinkedIn. I would like to show you also a list of references, but you will find that later on. And now I would like to thank you for your attention. I'm very happy to receive your emails and to answer your questions later on. Thanks for your attention and your interest.